So, OpenFlow version 1. Version was very simple. You had a table, you just match the entry, and
so we missed one slide.
this slide is not there.
Yeah, previous slide will be.
Yeah, that is gone. Don't worry about that. Whatever is gone is gone. These slides have been renumbered and redone. So you just follow the new one and don't take notes on the old one for a minute. I mean, at least you are transferred. So OpenFlow 1 had a very simple table, one table. Now there are many tables, 1.1, right? So the reason they need to do this is because they needed to support some new protocols that they had not thought about before, in particular MPLS. All right, MPLS has stacks of labels. You cannot look up all of them in one sweep, so you have to look them up by sequence of tables. And so the new concept is table chaining and group tables. What is table chaining? You look up in the very first table. If there is a match, it will tell you what to do and where to go. You go to that table. If there is a match, it will tell you what to do and where to go, and so on and so forth. Okay? Is that somewhat making sense? So that is the table chaining. Now, normally you have so many tables and tables. You have something called group table. And I'm going to talk about the group table in the next slide. But let's finish table chaining. On a match, instruction may be immediate action, which may be to modify a packet, update the match fields, and or update action set. So the actions are of two kinds. One is do now, do later. All right? So do now is immediate action, and do later is add to the action set. Add to your list of things that you need to do before the packet goes out. And then whatever, if you might change the match fields. For example, if you are matching with the top level stack, now it might say, take the second level stack out of the packet and match with that. So send the match data and the action set to table N. Here I should have set table I. It doesn't have to be the last table. Some other table. And so you continue like that. And so this is table chaining that allows you to handle the same packets by many different aspects, which is what they're in the MPLS stacks. Now there is one more. So there is an action set. And the action set is the list of things that you have to do, and that is you keep it in this set. So action set is 0 here. It becomes whatever was told here 1, and then 3, and then whatever. So you keep making your list of actions. Okay, group table. So I'm going to come to group table, but basically on a miss, the instruction may be to send the packet to the controller or continue processing with the sequentially next table. So if you went to table 1 and nothing matched, what do? You have basically, previously, I don't think in 1.1 they defined it. I think it is more clear in the next few slides. So there are several options. One is that you go to the table number 2, and if nothing matches, you go to table number 3 until you find a match. Or there might be or you send it to the controller and say, look, nothing is matching. What do I do with this packet? And now the group tables. Group tables basically are designed for BUM, broadcast, unknown, and multicast. So basically, previously everything was handled as broadcast. So you send it to everybody. But now you can be smarter, because the group table will tell you that you have to send it to these 5 places, right? And for every possible multicast address, they might have a different entry. So you go and match there and you say, okay, right, if you match this line, then you send it to these places. If you match this line, then you send it to these places. For the group table, each entry has a variable number of buckets. And if the bucket says all, then you execute all the buckets. And this is used for broadcast multicast. If it says select, then you select one particular bucket. Used for port mirroring. Selection may be done by hashing some fields. So basically, when you want to monitor a traffic, that is when we need the port mirroring, right? Everybody remembers port mirroring? Port mirroring is when the traffic is going X, but somebody wants a copy of it, right? Some manager wants a copy of all the packets. That is when we use port mirroring. So in that case, you can send it to one of the managers, and you select that based upon hashing of some fields. So, if there are many different places the packets are going to be mirrored, then you can select by hashing some fields. Indirect, and that one means execute one predefined bucket. Okay, so this one is switch selected, and this one is exactly. So this one will say, well, there are so many possibilities. You can pass on the first one. So many possibilities, and you select one. Here, the controller has already selected one for you. That's the main difference. Okay, and fast failover is execute the first live bucket. That means you use the first live port in that list. So sometimes the things may fail, the links may fail, and the group table will tell you if the link 1 is down, what to do with the packet. The link 2 is down, what to do with the packet. Okay, so they thought about some new problems that they had not seen before, and now they have group tables which can handle the multicast better, that can handle the port mirroring better, and that can handle the failover better. Alright, so with these features, they can support multipath, MPLS, Q-in-Q, and tunnels. So multipath is clear that if you have 2 paths, you could hash something and then select one of the paths. No, the select, switch selected. MPLS is basically multiple labels you can push and pop and go through table chaining. Q-in-Q, multiple VLANs, which is exactly similar to MPLS. You look at the first VLAN, and if you need to look at the second one, then you go to the second table. And tunnels. Now tunnels are VXLAN tunnels, NVGRE tunnels. VXLAN is most common, right? So it could be VXLAN, NVGRE, or one of those tunnels that we talked about earlier. So those are supported now, because you will go through the virtual ports. Now virtual port we didn't talk about here right now. Virtual ports were talked in OpenFlow version 1. Right? And you can go back to the previous list if you wanted to see the virtual ports. There are 7 virtual ports, and these are the 7 virtual ports. All, controller, local, table, normal, and flood. So this will take you through a tunnel port. So that is actually okay. So anyway, so this is virtual 1.1. Now here are things though. So with 1 and 1.1, they are not compatible. So the switches that run 1 cannot run 1.1. Obviously, they have no idea of multiple ports and multiple tables. All right. So that's a little problem in the sense that either people have not moved, so there are lots of version 1 switches, and they are taking time to get to the next version because this was an incompatible move. Any question about 1.1 before I go to 1.2 and 3 and 4? Did everything make sense here? That they have a table chaining and that they have group table. Those are the two things new. Yeah.
Explain the use of multiple tables.
Explain the use of multiple tables. So basically, previously you had one table, you matched to any matched, and if you matched with any entry, you did the action and you got out. Right? With that, you cannot handle multiple labels, because after the first label, you have to match the second label. So you have to go back to the table, right, again. Right? So that's why they have these multiple tables.
But can that table be referenced repeatedly?
Okay, so you don't, okay, that's a good question. The question is, can that same one table be repeatedly, can you go from table 1 to table 1? The answer is no. You always move forward in the table. From 1 you can go through to n, from 2 you can go to 3 to n, from 3 you can go to 4 to n. Alright? So that way you are guaranteed to finish. Otherwise you might be in a loop in the same table or in the same set of tables. So you are not allowed to go backwards. Good question. Yeah.
Multi-table is basically for implementing if then else in the data plane. So it is basically if you match something, then you go to table 2 or table 3, and it's like implementing if then else logic in the data plane.
Okay. So one example of what they said is that multiple table helps you do any if then else, right? If something happens, then you do table 2. If something else happens, you do table 3, right? So one of the examples of that is MPLS table. If the VLAN number, if this tunnel is ending here, MPLS tunnel is ending here, then you take out the label and do something with that packet. So it is general if then else. Any other question? Yeah.
So are we still store these tables within the controller?
Yeah. So the question is, are all the tables are still, actually you said stored, no. Are all the tables still programmed by the controller? The answer is yes. So the controller will send you n table plus group table. Okay?
So then where does this table be stored? In the switch or?
Oh, okay. The table are stored in the switch. The table itself are made in the controller, but they are stored in this. They are basically. I didn't want to use the word they are stored in the controller. A controller probably has a database which is much more general than just the table alone. And then when somebody asks, they just send the table to the switch, and the switch has it in a ready-to-use form where it can just go and look it up and go. So the answer is yes, they are stored in the switch.
Is this n parameter of the version, or is it the tables are created and destroyed?
Okay, n is a variable number. It's not nothing with the version number 1.1. Some switches might have 5 tables, some switches might have 1 table, some switches might have 100 tables. So the controller will tell you. Yeah.
The concept of table chaining looks like the linked list in the data structure,
Linked list, yeah.
right? And then, we go to the group table. I still cannot understand how is a group table organized.
Okay, so group table is table number n plus 1. All right. Group table is just the last table, except that it has a different structure. A different structure in the sense that it has multiple buckets, right? So that is explained in the next slide. The group table has multiple buckets, variable number of buckets, right? So, and then the instructions will tell you which of these things to do. Either you execute all the buckets, or execute a bucket, one of those, one of some buckets, or you execute ith bucket, things like that. So that is group table. You understand? So group table is the last table. You don't come back from the group table. However, in the group table is slightly different than the other tables. There is a group of actions.
So the group table has multiple buckets. That's a connection block.
Group table has multiple buckets.
Buckets. The bucket is connection blocks.
Bucket is action items.
It's action item.
Yeah.
Okay.
buckets are, each bucket is one action. Good questions, I like that, so please do ask. All right, 1.2. OpenFlow 1.2 added V6 support. So with 1.1 they could not handle V6 because basically to support any new protocol you need that to be defined in the tables. And that actually is a problem because the protocol is not self-extendable. I and you cannot extend it. It has to go through the ONF. ONF has to define the field and then we can use it. So they added IPv6, IPMP v6 and so on and so forth, ICMP v6. And they also changed the matches to be extensible matches, TLV values. Previously they were just fixed length that, if your MAC address is this and that, so on and so forth. Now the matches are defined by TLV, type, length and value. Is it a number? Match, for how long and what is the value, right? So the value is defined, this is the actual length of the value. Type, length and value. And experimental and extensions. So there were some fields which were especially specified for people to experiment with. These are not standard, but if you come up with a good use for it, then they come back next time and we will put it in. So these are experimental code points that are assigned by ONF, which are especially for the experimenter. 3 changes: IPv6, TLV, and experimenter. Okay, not much difficult. 1.3 went even further, lot more actually. So I have 2 slides on 1.3. In 1.3 they put the extension headers. So IPv6, those of you who know IPv6 know that it has many headers. This was supposed to be one of the special features of IPv6, which I don't think is such a good feature now, considered good. But you had the main header and then you had the extension headers which were optional, and you could have any number of extension headers and so on and so forth. That makes it slightly difficult to handle the things in hardware. But anyway, so extension headers. So now you can check hop by hop extension header, router extension header, fragmentation extension header, destination options extension header, authentication extension header, and ESP extension header. And if something else is present. So IPv6 needed more work. MPLS was handled okay, except that when the MPLS bottom of stack bit is set, then you are supposed to do something different, because when you're at the bottom of the stack, you cannot pop anymore. And so that handling was corrected. MAC in MAC. So they had already done Q in Q, but now MAC and MAC showed up. So MAC in MAC is handling. Now, can anybody think about what you need to do in MAC in MAC? What you may have to do in MAC in MAC? Anybody remembers what is MAC in MAC? Huh? No, Q in Q is different. MAC in MAC. Nobody remembers that?
It's provider's MAC address.
Yeah. And when you exit the provider, what do you have to do?
Encapsulate the address outside.
Yeah, you have to decapsulate basically. So the thing is, when you come in, the provider will encapsulate in its own MAC address and send it through its network. At the exit, you have to take out that encapsulation and the packet will go on the customer's MAC address. So that has to be handled, and that is handled now. Tunnel ID. Now, if you have a tunnel, then they need some idea, some information, VXLAN. So you have to say, well, it's not just sufficient to say that set up a VXLAN tunnel. You have to say, where does it go to? Right? So all that information has to be put. Per connection event filtering. So basically, the OpenFlow allows one switch to be managed by many controllers. Now, if suppose a link goes down, who should I tell? Right? And so now connection here means connection to the controller. Per connection event handling means that now they will tell, okay, if this happens, please tell controller number 1. If this happens, please tell controller number 2. The controller number will say, please tell me about all these events. If link goes down, that happens, this happens, packet overflow, buffer overflow. Any trouble you get into, you know which controllers to tell it to. You may have to tell it to more than one controller. So there is per connection event handling. Before that, they used to tell everybody, and some other software on the way had to figure out which controller to tell. Okay. Many auxiliary connections to controller to avoid to exploit parallelism. Now previously we had just one connection to the controller, and now we can have as many connections as you want, and you can send packets in parallel. You can do lots of things in parallel. You might have, for example, let's say 100 ports. Not really 100, maybe 10 ports. If you have 10 ports in a virtual switch, you happen to have something on the port 1 and something on port 2 and something on port 3, so you might have 5 packets to send to the controller. Previously they had to go in sequence, now they can go in parallel. Alright, now I'm just thought about something, that while they can get out of here in parallel in the software, once they reach a physical neck, they will go in sequence. But at least the bottleneck is not the software. Okay, here in software you can get out fast. Alright, better connection capability negotiation. So capability negotiation, what is capability negotiation? Basically when the switch comes up, the switch and the controller talk, and the controller asks, what are the things that you can do? Well, I can do version 1.1. That's a capability. Alright? Controller may not like it and say, sorry, I can't manage you, forget it. Or it may say, okay, alright, I manage you. So there is a negotiation also going on, right? So this is called negotiation, but it's basically capability discovery first place, right? And then negotiation. Or how many quality of service can you manage, how many queues can you manage, how many ports you have. So all of these are capabilities, right? Capability negotiation, now it can go into many messages. Previously, the whole thing used to go in one message, and which actually may not be a good idea, so that is better. More general experimental capabilities. Now experimental capabilities were allowed in 1.1, but people who were experimenting found out that they were not sufficient, so they are more general. A separate flow entry for table miss actions. So we talked about what happens when you miss a table. So it was left open as to what you do. Now it is not left open. In 1.3, the last entry tells you that if you miss all other entries, then you should do this. And this may be sent to the controller, go to the next table, go to the table 5, throw it away, whatever. So there is a very clear instruction for table miss. In 1.1 it was not. Cookies. The cookies field is to help the controller. Now what is cookies used for in the web server? Anybody knows why they use cookies? In the web server, yeah. Cookies are used in the web server, right? So it helps the server figure out, where were we before. It doesn't keep any state, right? Server doesn't keep any state, but if you send the cookie back, then it knows, oh yeah, this is Raj Jain's and he had a bucket number 5 where he was buying this stuff. All this information is with you, and the cookie is the only thing that tells them, and then with the cookie they can figure out everything. So similarly, they have a cookie here where when you send a message, it doesn't have to go figuring out the whole thing about that message, that packet, or whatever it is. There is a cookie which tells it that this is what this message is about. There is that backspace. Did I miss too many? Okay, cookies, yeah. A cookie field is added to messages containing new packets sent to the controller. This helps controller process the message faster than if it has to search its entire database. So now it can basically, okay, all right, this is a packet which is MPLS, and I got to look at what to do with the MPLS stuff. This is a packet which is about Mac and Mac. So something more context about the message is there in the cookie. Duration. All the counters have duration. So now all the counters have a timer which along with the count. So it is not that you find the number of packets sent and number of bytes sent. You have when the counter was initialized. So now you can calculate the rate. Right? And rate are going to be used in a minute. So I'm going to present that too in a minute. But so they need to have a duration. Per flow counters can be disabled to improve performance. Previously the counters were per flow, and you had hundreds and thousands of flows, and you had hundreds of thousands of counters, and this, people were busy counting than doing the work. Right? So they said, okay, all right, let's forget counting that much. So you don't have to have per flow. We could just do with the per port is fine, or per switch is fine in some cases. So basically per flow counters can be disabled. Per flow meters and meter band. But what do we have is actually counters can be disabled, but you might need it for some reason, and the reason is you have a meter and the meter bands. So what is a meter? A meter is something that measures the rate of something. Okay? And meter band is a threshold on that meter. So let me explain. So let's say a flow belongs to customer X, and customer X has paid for 18 megabits per second. So we want to make sure that they never send any more than 18 megabits per second. If they send more than 18 megabits per second, we throw away their packets. So how do you program this stuff? First of all, you ask the switch to measure, that is called a meter. You ask the switch to meter the rate, so it will have a duration, it will have a counter when initialized, and it will have some count, and then you can calculate the rate. The rate might be like this, red curve. And then there is a band setup. There would be more than one band setup. So if it is, this is band 1, this is band 2, band 3, band 4, you could have any number of bands. If the band is crossed, then there is an action. Alright? The action could be as simple as throw it away or start counting, and now we will charge him at a higher rate. Right? So there could be many other actions. Or it could be that please mark this other bit and send the packet so that somebody else can throw it away. Many different actions possible when you overflow your rate. Alright? So that's what it is. So these meters and meter bands. Meters are simply the rates, and the bands are thresholds. Nolan? Making sense to you? Okay. So what is a band? What is a band? I'm sorry, I'm not asking you, I'm asking Nolan. No, don't know? Yeah, so please pay attention. And you too, actually, I'm not sure. Jinji, are you paying attention to the class? Is it making sense? What is a band? Loudly.
It's a threshold.
Threshold, okay, good enough. Please pay attention. If you are in the class, I want you to pay attention, full attention here, okay, and not on the computer. Please close your computer down unless you need to see something which is related to the class. Okay, all right, go ahead. So, meter may have multiple bands, and meter is simply a threshold, right? Anybody has a question about that?
So there could be a lower band, a lower level also below which the bandwidth should not fall, or are they all upper bands?
No. So hold on. This is usage, not anything else.
Oh, this is usage.
Right? I mean, if you don't use it, and if you bought 18 megabits and used 2 megabits, then nothing can be done in terms of service. This is the actual traffic. So there is no minimum. Yes, I mean, there could be a thing that if it is here, then send the packet, don't drop it, things like that. I mean, maybe put it at a higher priority, so other people will get dropped, but not this one. Right? Yeah, you can do that too. Yeah. Now, on triggering a band, the meter drops the packet. If it drops the packet, then we call it a rate limiter. That's just an example. Right? If you want to implement a rate limiter, you just say that you triggered the band, drop it. Other QoS mechanism can be designed using these meters. Right now they have only one mechanism, which is rate limiter, but others will come in the future. Meters are attached to a flow entry, not to a queue or a port. So that's important to understand. Each flow has a limit, not a port or a queue. And multiple flow entries can all point to the same meter. So the way you get the queue or a port is possible by all the flows that are going to that queue can use the same meter. So they will increment the same meter, and the meter will represent the whole total rate. Right? And then all the flows will be dropped or whatever will happen to that queue. So, but meters are attached to a flow entry. So when you go back to the table, which is actually, I don't want to go back again, but the table entry is already shown here. Match fields, priority, counters, instructions, timeouts, and a second timeout, and then cookie. All right? And so in the instruction, it could be a meter with a meter ID, and then the meter band, and then the counter. And the meter band would be band type, the rate, counter, and a specific whatever you do. So there are many different kinds of bands, and there are right now two types of bands defined. One is drop band and one is remark band. If you cross the first band type, you are dropped. If you cross the second band type, then we remark the packet. What is DSCP? Anybody remember? Yeah? Differentiated services. Okay, this is diffserv. That was your question?
Yeah.
Okay, all right. DSCP is diffserv. Yeah, go ahead. What is your question?
My question is OpenFlow is which layer is used? I mean, is OpenFlow is layer 7 application layer? Is a protocol?
Okay, the question is what layer is OpenFlow? OpenFlow, actually, let me see. You can implement any set of layers with OpenFlow. So far, we have seen layer 2, 3, 2.5 MPLS, 3 IP, and something related to ports, because ports are in that match field. So up to 2 to 4 we can implement very easily. Now, having said that, the port numbers in the layer 4 header, like port 80, right, L4 port, gives you some idea of the application. That is a web application. So you can even control that. So in that sense, it is basically, not related to a layer, it is just related to the whole, basically how you define the flow, open flow. Flow can be defined up to layer 4, can be defined for the higher layers.
So my question is the communication between host and controller. So there is protocol, this is OpenFlow protocol.
Yeah.
Which layer is used?
Okay, so the question is that OpenFlow is the protocol which is used between the switch and the controller. Which layer it is? So in that packet, it will be an application. Basically, you will take the OpenFlow message, put it inside TCP, put it inside IP, put it inside Ethernet, and send it. Right? So the OpenFlow, and this is true for all other protocols that you will see here. When people talk those protocols other than OSPF and other things, those are different things. Those are not, right? But any of these control protocols that we say, those are messages basically, and they are application. Okay? Any other question? Just like DNS. If you were to send a DNS request, that would be an application message. Right? You will take a DNS request, put it into a TCP and send it, actually UDP and send it. And you'll get a response. Yeah.
For the meter rate, does it also count the traffic between the switch and the controller?
Does the meter count the traffic between the switch and the controller? The answer is most meters probably will not be wasting their time doing that, because it's like, how much you talk to your boss, there's no limit. And it's really for the controlling other people's traffic. I mean, you could put a limit, but that would just not allow you to work at all. Yeah.
In the case of dropping the packet, so after we drop the packet, do we lower the sending rate? Like, do we drop the packet and lower the sending rate?
All right. So the question is, if the packet is dropped, do we lower the rate? Actually, you didn't lower the rate. You didn't count the packet as sent, so the rate is not gone up. So what will happen is, in this diagram, this will be clipped off. Right? The number of packets, actually it won't be clipped off. What will happen is, at this point, you will drop the packet and counter will remain the same, but the time will go up. Right? So the rate will go down in that sense, right? And at some point, you will be able to send one packet.
So it's like congestion avoidance.
It's like congestion control actually. It's not avoidance, because you're dropping the packet. When you drop something, that is not avoiding anything. That is actually killing it. So yeah. Avoidance would be when nothing is lost. When you store it. Yeah, you could store it here too. Basically, but the queue will build up very fast and then you will have to overflow. Yeah, if you did store and things like that, then it will be avoidance.
So the difference is more like retransmission, right? In this case, there's nothing taken care of the retransmission.
Right, if you drop it, you don't retransmit anything. Basically, the source retransmits it. If the source has a TCP, we don't know whether this is TCP or not, right? If the source has TCP, it will retransmit. If it has something else, it may not retransmit.
In this case, it's not, right? There's no retransmission.
No, the switches, the switches don't do any retransmission.
Okay. Then, his question is about the classic problem in the congestion control, internet, right? In that case, if you drop and you fail some of the transmission, you do retransmission, then you lower the rate. That's not the case?
No, hold on. Let's talk about the standard non-OpenFlow network, internet. In the internet, there is no retransmission. Now, there are some exceptions that I'll come to in a minute. In general, there is no retransmissions along the way. Retransmission is done only by the source. Okay? The exception is the wireless network. In the wireless networks, the packets are thrown out so often that it is not fruitful to have the source retransmit them, because if we are 2,000 miles away from the source, you might as well retransmit it rather than wait for the source. So the wireless hops and wireless protocols such as Wi-Fi, they have retransmission per hop. Right? That will continue here as well. That has nothing to do with the OpenFlow or anything. So most of the non-wireless hops there is no retransmission. Most of this. And again, you could design a protocol which could retransmit it, such as token ring. But token ring is gone. So the only thing mostly people use is the Ethernet. Ethernet doesn't do retransmissions. Okay? All right. So we understand the band and rate. Now, OpenFlow version 1.4 just came out last month, actually October, so 2 months now. And 1.4, the key reason was optical networks. Now, what is an optical network? Now, you guys have not been taught optical networking. It's just not possible to teach all that in a course here. But there are switches nowadays that do optical switching. So basically, you can program them so that the light which is coming at the red light which is coming on this one goes to that fiber, the blue light goes to that fiber and the green light goes to this fiber. So depending upon the color of the light, you can send them in different direction. And so that is basically allows you several gigabits, even 100 gigabits of traffic to go very easily. You're not looking at the packets, you're not looking at the headers, you're just looking at the color of the light. And that can be done with a prism. Prism can easily, separate out red from the blue. Right? So it's very easy. So those optical networks can be controlled by OpenFlow by just telling the switch that, okay, now, please send the red light this way, blue light that way, green light this way, on fiber 1, on fiber 2 do this, fiber 3 do that. So for all these fibers, for all these colors, the light can be sent to the right place. It's actually much better and much easier than packet switching. So people used it, some experimenters may have used it, and now it is a part of the standard.
Are you here limited to 3 types of packets?
Here you limited to?
3 types of packets.
Types of packet?
Yeah, 3 types.
3 types.
Because you have 3 colors.
Oh, no, okay. The question is, because you have 3 colors. No, actually, first of all, they don't have red, blue, and green, by the way. I just made it as an example. The light that is used is not visible light. All right? And you can use 64, 128. The number keeps going up. Basically, how many wavelengths can you use in a fiber is a matter of how good optics we have. And that keeps going. So previously we used to have 4 wavelengths, then 16, 28, 128, 1024. Now I lost track. It could be 4000 by now. I don't know. So basically what happens is the more wavelengths you define, basically all you're doing is light is a spectrum. Light is like wireless. So you have to define wavelength is nothing but a channel width. So you define how fine light can you differentiate. You see, if you take lights which are very close, they may not be very far by by the time you differentiate them, they might all fall in the same place, right? So that is what it is that channel width decides how many wavelengths you have. And so you could have that many circuit on one fiber. Okay, and this is all circuit, by the way, not packets. This is all circuits. Everything that goes out. We don't look at the packets. We don't convert the light into electronics at that point. All right. Any other question? Optical ports. And then rest of it is very small. Rest of it is improved extensibility. Now TLVs were not enough, but then some places they didn't use it before. Now it's all complete extendable. Experimental extension has been extended. More information is sent when the packet is sent to the controller. So for example, it says the reason I'm sending you is because it didn't match, because the TTL exceeded, because whatever happened. So now the controller doesn't have to guess why the packet came in. Controller can select a subset of the flow tables for monitoring. Switches can evict entries of the lower importance if table full. So that's another thing. You saw in the previous, here there is a priority field. Actually, priority field is used so that, if you match 2 entries, you take the higher priority one. So I should probably go back again. So, but what happens is, suppose the controller sends them, 2000 entries and they only implement 100 entries. What do? So they will have to get rid of some flows that have not been used for a long time. So the flows that are not used will get out, and then what will happen is the packet do come in on those flows, they will be sent to the controller. Switches can notify controller if table is getting full. And so that is another thing, is that you don't have to wait until you are almost ready to die. You just have to tell, well, I'm 90% full, please tell me something. atomic execution of a bundle of instructions. So that is another thing. Is that anybody remembers what is atomic means? We talked about that in the database discussion.
Can't get divided.
Eh?
No. Reading database is the quality of database.
The quality of database is what? Acid was the quality of the database, but what was A for atomicity? What does atomic action mean? Yeah, do it or not do it completely. So suppose I tell you, please go there, pick up the cup, fill up with the water and bring it here. 4 actions, right? Now atomic action means that if you go there and pick up the cup and then that's it, you don't find the water, what do? No, return the cup where it was so that nothing has changed and come back. So you didn't do anything. Right? Until you finish the whole thing, the action is not done and nothing in the world has changed. If you have to stop in the middle of the action, return the whole world back to where it was. That is what is called atomic. Atomic means you cannot divide it. You cannot do half of it. Make sense? Everybody understands atomic now? Alright, so that is now possible to do in OpenFlow. You could have 5 actions, but they are atomic, in the sense that the whole group has to be done or nothing has to be done. Alright, so now here is the summary. The summary is version 1 was single flow table and just handled the Ethernet and IPv4. 1.1 did MPLS, Q in Q, efficient multicast, ECMP, and therefore required multiple tables. 1.2 did IPv6 and the TLV matching and then also allowed multiple controllers. 1.3 did MAC in MAC, multiple channels between the switch and the controllers. There is 1.3.1 and 3.2. Both of them are bug fixes. This line should go to 1.3.1. I always forget to bring my pen. So, all right, and 1.4 is OTN. What is OTN? Optical Transmission Network. All right, and experimentals, bundles, and table full. Any question about any of the versions? Okay, what does table full mean? So when you get a new entry, suppose you got a packet and you sent it to the controller sent you a new flow entry, but your table is already full. So you have to do some kind of LRU. LRU means what? Least recently used. And replace some entry with this new entry. Right? That is what table full means. You can evict. Here the word evict means throw out that entry and put this new entry there. Okay? All right. So now we know all about OpenFlow. So we move on. Bootstrapping. You have a question?
What's the error in the version?
Line is going to.
Okay, what is the correction? The correction is that this line, the bottom line here, bug fix would go to 1.3.1. And 1.3.2 is also bug fix. So if you go to the website, which is mentioned all the way through everywhere, you will find all these standards. You will find 1.0, 1.1, 1.2, 3, 1, 3, 1, 3, 2, and 4.
So currently, which version from vSwitch support now?
Okay, so the thing is, everybody is at different version. All right, every manufacturer, everybody is at different version. Obviously, nobody is at 1.4 right now because it came out in October, right? Most people are at 1. Now, having said that, there are people who are coming to 1.3. All right? So, I mean, basically, if you were to buy a software, piece of software, or piece of hardware, or whatever it is, the first thing you ask is what OpenFlow version you support. Right? Because they're so different. If you get 1.0, it will not support, I mean, basically you cannot extend it to 1.1 or anything like that, right? I mean, software can always be replaced, but if it is hardware, there is any hardware, it cannot do 1.1. You have to throw away that hardware and get a new hardware.
So I have questions. One of the questions is,
Yeah.
if I want to buy just the switch, it supports OpenFlow. So they support controller as well, or just only switches?
Okay, the question is, if I want to buy a switch, OpenFlow switch, can I just buy the data part or do I need the controller too?
Yeah.
Okay, all right. So the answer is you need both. You will need a controller, preferably, sitting is still, it is multi-vendor world. It's much more compatibility than if you buy a controller from Cisco and buy a switch from Juniper. That's kind of difficult. But here, so you will need to buy a compatible controller. So if you buy a switch which supports 1.3, you better buy a controller that supports 1.3.
Cisco sells the controller unit.
So this question is, does Cisco sell the controller unit? Yes. All right. So basically everybody that we know of nowadays sells a controller and a switch, and then you should basically match the version numbers. All right. Huh?
The idea of separation was to have a controller which kind of proprietary, but the switches should be like commodity because they are just forwarding and switching devices.
Yeah.
So they should be actually compatible with all kinds of controllers.
Right. The version number. So here I think though, this is just a new protocol, and we are all learning, and they're all learning. And so they didn't think about all of this, and now they had to make a jump here, such that the old this is criticism of OpenFlow by some people, is that OpenFlow is software defined, but if you are implementing it in the hardware, it is hardware defined in the sense that you cannot use the old hardware, right? Which is a weakness, right? It should be, in the ideal world, this all should be very smooth. You just need a firmware upgrade from your vendor and you are done. But it's not a firmware upgrade. If you had one table in the hardware, it cannot make n tables right away. That's not a firmware upgrade. That's a hardware upgrade. So that's why I discussed that in great detail as to what happened at 1.1. Everything else after that is sort of firmware upgrade. All right, let's move on to bootstrapping. So bootstrapping is how does somebody come up? So when the switch is turned on, the power comes on, it should have three pieces of information. It should know what is its IP address, who is its boss, and what is its default gateway. All right? And that is the same thing that when you bring up your computer, turn on the power on your laptop, it needs to know what is its IP address, what is its DNS address, and what is its gateway. Right? So how does it get? How does your computer get it? Either you put it in and then doesn't change, or you do DSCP. And so you need a DSCP protocol for OpenFlow. And that protocol is coming up right next to it in a minute, in the next slide. But anyway, let's say given that the OpenFlow switch has gotten these three pieces of information, then it can connect to the controller and say, okay, all right, here I am. I want to connect to you and tell me what should I do, what my table I should fill up my table with. And then the switch provides the configuration information. It tells that I have 5 ports and this blah, blah, blah. And then the controller installs a rule to forward LLDP responses. Now, what is LLDP? Anybody remember LLDP? Yeah, go ahead, loudly, if you are sure. Yeah, discovery protocol. So, link layer discovery protocol, LLDP. Basically, by sending this, you can ask your neighbor what is your speed, whether you support link aggregation, anything else that you wanted to know, whether you support this feature, do you support Q and Q, do you support blah and blah, all that, right? So that is a link layer discovery protocol. So there will be one rule installed that says that if you get an LLDP response, it should be sent to the controller. And then it says in the next message that says, please send an LLDP request to all ports. So it sends the LLDP request to all ports. The messages come in, it does the matching, and the matching says send it to the controller. So all the responses go back to the controller. Now the controller knows what you are connected to, where you are in the world, what are their speeds, what are their capabilities. You have already told your capabilities, but now I know your neighbor's capabilities. And so now I can tell you exactly how to do your forwarding. Controller determines the topology from the LLDP responses. So that should be obvious. So basically what this part has done is that the controller has exchanged the information about you and your neighbors. Yeah.
So here the neighbor means controller or switches?
Okay. The neighbor means, the question is the controller means, the neighbor means controller or the switches. It really means the switches. Although an LLDP response will go, question will go to the controller also, because if it says to all ports, it might go to the controller also. But really, what it really wants to know is these other neighbors. Any other question? Yeah.
But the LLDP's request is sent by the controller or the switch.
Okay. So the LLDP is sent by the switch. Yeah, but it could be very easily implemented by sending some packet to the switch which says, instruction says, when you get this packet, please send out LLDP request to all.
Oh, so if the controller tells it to send the request.
Yeah.
Right?
Yeah, so controller basically tells it to send the request.
This way, I think LLDP won't go back to the controller because it tells it to do.
Yeah, if there is a rule already installed. First rule is that if you get a response, send it to the controller.
Yeah, I mean, he was talking about the controller getting the LLDP request.
Yeah.
I don't think the controller will get that because it tells the switch to do that. So.
No, here is the thing. No, let me tell you. I mean, I could be wrong on this one. This is a fine point, and it really doesn't matter. But the idea is there are 7 ports defined. 7 ports defined. All, controller, local, table, normal. All right? And flood. So the action might be to send to all, except the incoming interface. So maybe, it depends on how the action is sent, how this LLDP request message, maybe, this is the detail that I will have to go and look into the code, is that it is quite possible that it is sent by the controller saying that, okay, forward it, and then it says, the instruction says forward it to all except the incoming, in which case it will not go to the controller.
Yeah, that's what I mean.
Right? And it will go to all other places, and then the other instruction says when you get the responses, it will go back to the controller only, right? So that is one way, and I think that is how it probably does. Yeah, go ahead.
I think it would be different because the controller installs the root once, and that activity takes place a number of times. So incoming interface is from a neighbor who's sending an LLDP request not from a controller. So it will not be sent only to that port. It will not be sent to the neighbor who is actually sending it. So it might go to controller actually, because it is going to send on that port.
Okay.
There is
All right. So here thing, I am glad that you guys are arguing this, because now you understand. And for those of us who really have to really resolve this, we'll have to read the code, and which is none of us actually at this point. But the idea is that there are two possibilities. One is that the request starts from the controller, and like any other packet, that packet is seen by the switch, and then it says what to do with this packet, and it says, okay, send it to all. And so that is one way. Second way is that it could be just an instruction. Somehow it gets to the switch, and I don't know how it gets to the switch. And then the switch says, okay, all right, I have to execute this instruction, which means send to all. In this case, it will send that to controller also. And since we don't have the details, I would stop it right there, right? Happy, everybody? Happy with that resolution? I don't, yeah, go ahead. You have a solution?
So, I don't know specifically about LLDP, but what happens in ARP is like, when suppose a particular host sends out an ARP request, and which is a switch, and the switch does not, what it says that there is a default rule in every OpenFlow switch that says that if you don't have a matching flow entry for this particular flow, send it to the controller. And so the ARP request goes to the controller sends back the ARP reply, and switch sends the ARP reply to the host. So basically, the default matching request is that if nothing matches.
Yeah, but the example that you are taking, Sivarthi, is the ARP request started from somewhere else. The question people are asking is, where does the LDTP request start from? Does it start from the switch, or does it start from the controller? That's the question. If it starts from the controller, the responses do not have to go back to, the controller does not have to respond to it. If it starts from the switch, then the controller has to respond to the LLDP request. Right? Okay, so that's the part we don't know. We don't know where the LLDP request starts from.